Exploratory data analysis, EDA. Exploratory data analysis, EDA, is a data analysis approach aimed at understanding and summarizing the key characteristics of a dataset. It involves using statistical and visualization techniques to explore data, identify patterns, detect anomalies, and gather insights before conducting formal modeling or hypothesis testing. Primary goals of EDA. 1. Data familiarization helps researchers understand the dataset structure, size, format, and relationships between variables. 2. Data cleaning identifies and addresses missing values, outliers, or inconsistencies to ensure data quality and reliability. 3. Data visualization uses tools like histograms, scatterplots, box plots, and bar charts to uncover distributions, patterns, and trends visually. 4. Descriptive statistics summarizes data with metrics like mean, median, standard deviation, and percentiles to describe its central tendency and variability. 5. Feature selection identifies key variables that contribute to predictive tasks, reducing dimensionality and improving model performance. 6. Hypothesis generation forms hypotheses about relationships between variables for further statistical testing. EDA is vital in the initial stages of data analysis, offering insights, revealing patterns, and shaping subsequent steps. It supports informed decision-making and effective communication of findings to stakeholders. Exploratory data analysis, EDA, involves a variety of statistical and visualization techniques to gain insights and understand the main characteristics of a dataset. Here are some commonly used techniques in EDA. Statistical techniques. Descriptive statistics. Descriptive statistics provide summary measures to describe the central tendency, dispersion, and shape of the data. These include measures such as mean, median, mode, standard deviation, variance, and percentiles. Correlation analysis. Correlation analysis measures the strength and direction of the linear relationship between two variables. Common correlation coefficients include Pearson correlation coefficient and Spearman correlation coefficient. Hypothesis testing. Hypothesis testing is used to assess the statistical significance of relationships or differences in the data. Techniques such as t-tests, chi-square tests, ANOVA, analysis of variance, and non-parametric tests are commonly used. Outlier detection. Outliers are extreme values that deviate significantly from the rest of the data. Various techniques such as z-score, modified z-score, box plots, and scatterplots can be used to detect and handle outliers. Measuring data similarity and dissimilarity. There is a fundamental task in machine learning and data analysis. There are various techniques and metrics available for this purpose, depending on the nature of the data and the specific problem at hand. Here are some commonly used methods. Euclidean distance is a popular measure for continuous numerical data. It calculates the straight line distance between 2 points in a multidimensional space. The smaller the distance, the more similar the data points are. Mahalanobis distance is a metric that takes into account the covariance structure of the data. It measures the distance between a point and a distribution, accounting for the correlations between variables. Mahalanobis distance is useful when dealing with multivariate data and is particularly relevant in outlier detection. Cosine similarity is often used to measure the similarity between two vectors in high-dimensional spaces. It calculates the cosine of the angle between the vectors, disregarding their magnitudes. Cosine similarity is frequently used for text data analysis, such as document similarity or recommendation systems. Jagged similarity is a metric used to measure the similarity between two sets. It is defined as the size of the intersection of the sets divided by the size of their union. Jagged similarity is commonly applied in areas like text mining, social network analysis, and collaborative filtering. Hamming distance is a measure used to quantify the dissimilarity between two strings of equal length. It calculates the number of positions at which the corresponding elements are different. Hamming distance is often used in DNA sequence comparison and error detection. Edit distance, also known as Levenshtein distance, measures the minimum number of single-character edits, insertions, deletions, substitutions, required to transform one string into another. It is commonly used in spell checking, DNA sequence alignment, and natural language processing. Correlation coefficient measures the linear relationship between two variables. It ranges from -1 to 1, where -1 indicates a strong negative correlation, 1 indicates a strong positive correlation, and 0 indicates no correlation. Correlation coefficient is often used to measure similarity between time series data or feature correlation in feature selection. Manhattan distance, also known as taxicab distance or city block distance, is a distance measure that calculates the absolute differences between the coordinates of 2 points in a grid-like system. It is called Manhattan distance because it reflects the distance a taxicab would have to travel along the city blocks to reach from one point to another in a city with a grid-like street layout. Minkowski distance is a generalized distance measure that includes both Manhattan distance and Euclidean distance as special cases. It allows you to control the degree of distance calculation through a parameter called the order or p. When p equals 1, it becomes equivalent to Manhattan distance, and when p equals 2, it becomes equivalent to Euclidean distance. Supremum distance. Supremum distance, also known as Chebyshev distance or chessboard distance, is a distance measure that calculates the maximum absolute difference between any pair of coordinates of 2 points in an n-dimensional space. It represents the distance between the points by considering only the largest difference along any dimension. These are just a few examples of the many similarity and dissimilarity measures available in machine learning and data analysis. The choice of metric depends on the specific problem and the characteristics of the data being analyzed. Visualization techniques. Histograms display the distribution of a single variable by dividing it into bins and showing the frequency of data points in each bin. They reveal the data's shape, central tendency, and spread. Or box plots visually summarize a variable's distribution by showing the median, quartiles, and potential outliers, useful for comparing groups or categories. Scatterplots illustrate relationships between two variables by plotting data points on a graph, highlighting patterns, trends, or correlations. Heatmaps represent data values using colors in a matrix format, ideal for visualizing patterns, relationships, or clusters in multidimensional data. Bar and pie charts. Bar charts use bars to represent frequencies or proportions of categories, while pie charts divide proportions into slices of a pie. Line plots show trends or patterns of a variable over time or along a continuous axis, often used for time series data. Scatter matrix, a grid of scatter plots showing pairwise relationships between multiple variables, enabling quick identification of patterns or correlations. These are just a few examples of statistical and visualization techniques used in EDA. The choice of techniques depends on the nature of the data, research questions, and the insights sought from the analysis. EDA allows analysts to explore data from multiple angles, identify patterns, and generate hypotheses for further investigation. Data visualization. Goals of data visualization can be summarized as follows. Data exploration. Data visualization helps in exploring and understanding the underlying patterns, trends, and relationships within a dataset. By visualizing data, analysts can quickly identify outliers, clusters, gaps, or anomalies that might not be apparent in raw data alone. It allows for a deeper understanding of the data and generates insights that aid in decision-making. Pattern recognition. Data visualization facilitates the identification of patterns, trends, and correlations between variables. Visual representations such as scatterplots, line plots, or heat maps enable analysts to detect relationships, dependencies, or changes over time. Recognizing patterns is essential for making informed predictions, identifying potential causes and effects, and understanding complex systems. Communication and presentation. Data visualization is an effective means of communicating complex information and findings to a broader audience. Visual representations are often more accessible and engaging than raw data or statistical summaries. By presenting data visually, analysts can convey insights, tell compelling stories, and make data-driven arguments that are easily understood by stakeholders or decision-makers. Decision-making and insights. Data visualization supports data-driven decision-making by providing clear and concise visual representations of information. Visualizations enable analysts to explore different scenarios, compare options, and evaluate the potential impact of decisions. They highlight key findings and insights that inform strategies, policies, or actions, ultimately leading to more effective decision-making processes. Explaining complex concepts. Data visualization simplifies complex concepts and makes them easier to understand. By representing data visually, abstract or intricate information can be presented in a way that is intuitive and accessible to a broader audience. This is particularly valuable when communicating technical or scientific information to non-experts. Identifying data quality issues. Data visualization can help identify data quality issues such as missing values, outliers, or inconsistencies. Visualizing data allows analysts to visually inspect the data for errors or anomalies, enabling data cleaning and quality assurance processes. By identifying and addressing data quality issues, the accuracy and reliability of subsequent analyses and interpretations can be improved. In summary, data visualization is essential because it enhances data exploration, pattern recognition, communication, and decision-making. It enables analysts to gain insights, identify relationships, and communicate complex information effectively. By presenting data visually, it improves understanding, facilitates the detection of patterns or anomalies, and supports evidence-based decision-making processes. Best practices for data visualization. Effective data visualization ensures clarity, impact, and accurate representation of information. Here are key principles to follow. Select the right visualization. Choose charts, graphs, or diagrams suited to the data and message. For example, use line charts for trends, bar charts for comparisons, and scatter plots for relationships. Ensure accuracy in representing the data. Know your audience. Tailor visualizations to the audience's expertise and familiarity. Use appropriate types and provide explanations for better comprehension. Simplify complexity. Highlight key insights by avoiding clutter and excessive detail. Use concise labels, titles, and annotations to guide interpretation. Emphasize key points. Use visual cues like color, size, or position to draw attention to important data. Add titles or captions to underscore significant findings. Scale appropriately. Ensure axes and legends accurately represent the data range, avoiding distortion or misleading interpretations. Provide context. Include labels, units, and sources. Add relevant context like time frames or locations to improve understanding. Thoughtful use of color. Use consistent, purposeful color schemes to enhance visuals and ensure accessibility, including for colorblind viewers. Encourage interaction. Incorporate interactive features like tooltips, zooming, or filtering to allow deeper exploration of the data. Test and refine. Gather feedback from users or stakeholders to improve clarity and usability. Refine visualizations iteratively. Maintain organization. Keep visuals neat and consistent. Avoid unnecessary elements like excessive grid lines or decorations that detract from the data. By following these practices, you can create compelling and effective data visualizations. Data visualization best practices: affordances, acceptance, aesthetics, and accessibility. Affordances. Effective data visualizations leverage affordances to ensure users intuitively understand how to interact with them. Visual elements such as buttons, legends, and icons should clearly indicate their purpose and functionality. Interactive features like hover effects, clickable areas, or tooltips help guide users and enhance usability. Consistency in symbols, icons, and design elements reinforces familiarity and reduces confusion, allowing users to focus on the data insights. Acceptance. To ensure acceptance, visualizations must align with audience expectations and preferences. Consider cultural and contextual relevance when designing visuals, as familiarity with certain styles can foster trust and understanding. Using widely recognized visualization types helps users feel more comfortable and confident in interpreting the data. Incorporating feedback mechanisms and adapting based on user input ensures the design remains user-centered and effective. Aesthetics. Aesthetic appeal plays a crucial role in creating engaging and professional data visualizations. Utilize harmonious color schemes, clean layouts, and balanced spacing to make visuals visually pleasing without overshadowing the data. Avoid clutter or excessive decorations that may distract from the core message. Thoughtful use of fonts, colors, and styles enhances readability and ensures the visualization conveys professionalism and credibility. Accessibility. Accessibility is essential to ensure that visualizations are inclusive and usable by a diverse audience. Use color palettes that are friendly to colorblind users, such as those recommended by ColorBrewer. Provide alternative text descriptions or labels for key elements to assist users with visual impairments. Interactive visuals should support screen readers and keyboard navigation, enabling all users to access and interpret the data effectively. By integrating these principles into your design process, you can create data visualizations that are functional, accepted by the audience, visually appealing, and inclusive. Gestalt principles and their relation to data visualization. Gestalt principles are psychological concepts explaining how humans perceive patterns and organize visual elements into meaningful wholes. These principles, originating from Gestalt psychology, highlight how our brains group and interpret visual stimuli, often based on proximity, similarity, continuity, closure, and figure-ground relationships. These concepts are highly relevant in data visualization, as they influence how viewers interpret and engage with visual data. Key Gestalt principles in data visualization. Proximity. Elements close to each other are perceived as related. In data visualization, grouping related data points or components, e.g., legends near charts, improves clarity and comprehension. Similarity. Similar visual properties like color, shape, or size suggest relatedness. For instance, using consistent colors for the same category across a bar chart emphasizes their connection. Continuity. The mind follows continuous patterns or flows. Line graphs leverage this principle to guide the viewer's eye along trends or relationships. Closure. The brain fills in gaps to create complete shapes or patterns. Simplified visuals or partially outlined elements rely on this to suggest missing details without overwhelming the design. Figureground. Differentiating the main subject, figure, from the background enhances focus. Effective use of contrast in data visualization directs attention to key insights while avoiding distractions. Common fate. Elements moving in the same direction are seen as related. Animations or patterns that evolve similarly can highlight trends or correlations in interactive visualizations. Relevance to data visualization best practices. Simplify complexity, grouping related elements, proximity, and using consistent styles, similarity, reduces visual clutter, making insights clearer. Highlight key information, contrast, figureground and alignment, continuity, ensure the most critical data stands out. Aesthetic design. Harmonizing colors and shapes enhances the visual appeal while leveraging Gestalt principles like similarity and closure for intuitive comprehension. Encourage interaction. Interactive elements that follow Gestalt principles, e.g., animations with common fate, make data exploration more engaging and meaningful. By applying Gestalt principles, designers can create intuitive, visually appealing, and impactful data visualizations that align with human perception, ensuring data insights are effectively communicated. To make data visualization more explanatory than exploratory, the goal should be to guide the viewer through the data with clear, concise insights rather than allowing them to uncover patterns independently. This can be achieved through focused storytelling, where the visualization follows a narrative, highlighting key findings and trends with the help of annotations, titles, and subtitles. It's important to keep the data focused on the most relevant points, avoiding visual clutter and using elements like color, size, or position to emphasize critical information. Providing adequate context is essential. Labeling axes, offering benchmarks, and explaining the significance of the data allows viewers to understand what the data represents and why it matters. Breaking down the data into digestible step-by-step insights ensures that the viewer isn't overwhelmed and can follow the thought process behind the conclusions drawn. Annotations, such as arrows or call-out boxes, can help direct attention to important trends or outliers. A clean, simple design, free from distractions like excessive grid lines or unnecessary 3D effects, is key in making the visualization more explanatory. Predefined filters or selectors that narrow down the data also help in keeping the focus on the main insights, removing the need for viewers to explore the data themselves. Comparisons, such as side-by-side charts or baseline references, provide context and highlight differences, making it easier for viewers to understand the implications. Consistency in visual cues, such as color schemes, shapes, or sizes, ensures that the viewer doesn't need to guess the meaning of different elements. Additionally, offering interactive explanations through tooltips or pop-up details further enriches the user experience, providing clarity without overwhelming the viewer with too much information at once. By following these principles, data visualizations can effectively guide viewers to the insights you want to communicate, making the data more understandable and actionable.